Hello everyone. I think we just finished the lecture series in nucleophilic substitution of type SN1 and SN2, and the lectures are in the previous videos I just posted. Now in this series what I'm going to do would be just to give you really the summary of the chapter through a selected number of questions that I would be solving in the nucleophilic substitution SN1 and SN2. I really advise you to go through this video and understand all of the problems that were solved in this series, and you'll be able to just be mastering the subject of nucleophilic substitution. This problem solving session will give you an idea of the mechanism of the reactions, the solvent types, protic, aprotic ones, the type of electrophile we have, meaning that primary, secondary, tertiary, carbocations, mechanisms of the reaction, rate of the reaction, and so on. So this is really a comprehensive problem solving session that is very valuable to help you understand what the substitution reactions are. So with that, I just go to the first problem here on the board. The question is asking us, draw the substitution products when an electrophile, which is the alkyl halide, a primary alkyl halide by the way, is reacting with one of these nucleophiles. The nucleophiles are given, and the question is just to give the substitution product. So without going to details of the mechanism of the reaction, we can just give what products are possible with these nucleophiles. So anything which is listed from A to E, F are the nucleophiles. The electrophile, because this is where the carbon would be attacked, that is the leaving group. It's a bromide leaving group. This is 1, 2, 3, a 4 carbon bromobutane. We call it 1 bromobutane because it has 4 carbons. Okay? So with this, the first one is easy. It is a strong base and a strong nucleophile. Hydroxide ion, an ion, has OH minus, has a negative charge, fully negative charge, so it's a very strong nucleophile. So the substitution product would look like CH3, CH2, CH2, CH2OH. That means just substituting the OH, the bromine by OH. That's for question 1. The next nucleophile is a cyanide. This comes, for example, as sodium cyanide, potassium cyanide, so don't be confused if you are just given, for example, in the question, somebody can give you just a salt, but you should know what the nucleophile is. The potassium is just a spectator ion, so when positive 1 is removed, the negative would be on cyano. So that's cyano. Here it's also could be sodium hydroxide or potassium hydroxide. Okay, now the substitution product for this would be just the whole of it, and a cyano group would be attached on that. So I'm not considering any mechanism right now because we are not deep into that problem yet. So I'm just giving you the substitution product, the nucleophile and electrophile. So just introductory questions. Here you have a carbanion. This is a very strong base and also a strong nucleophile because it's carbon-based nucleophile. So it may be not something you haven't seen before, but when this acidic proton is taken away, so this must have been produced from this. This is acetylene. When acetylene is treated with a base, one of the hydrogens would be gone because it's very acidic. It produces a very strong base or nucleophile. So that's the negative charge. So the product that would form is CH2, 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 and CN. So you have introduced an alkyne. This is an alkyne, a functional group, by the way. So that's the product. This is A, B, C. For D, it's water. Water is, even though it's a very strong, even though it's a very weak base, because it has a lone pair of electrons, sometimes it acts as a nucleophile. It is, even though it's a very weak nucleophile. So the pair of electrons on oxygen, which are available for attack that carbon right there, would produce over, like by heating and all that, it could generate a substituted product. But the substitution product looks like this. One thing you have to know, when it attacks and the bromine leaves, by the way, all of them have Br minus here as leaving group, Br minus. Okay? So water is a weak nucleophile. It can replace bromide, but as a nucleophile, that's what it does. But overall, this is not very stable because one of the hydrogens become more acidic proton. Therefore, if bromine comes and takes away one of the hydrogen, it would actually be the final product. Don't be confused, would be CH2OH, and HBr would be formed because one of the proton, because as a positive charge, it may not be stable, but a neutral molecule like this, after substitution, would be like this product. So here the product is an alcohol, here is a nitrile product, here is an alkyne product, here it is an alcohol product. So A and E are an alcohol. Here also it gives you the sodium iodide. You know that the sodium iodide is sodium plus and I minus. So you actually use just the I minus, which is a nucleophile. So the sodium, as I already was mentioning, all of this can come as a salt. But the positive counter ion is not part of the substitution reaction. Obviously, it is a positive charge. Because this is the electrophile, it only reacts with the nucleophile. So F would be CH3, CH2, 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 iodide. So it's an iodoalkane. We generated another alkyl halide. So by just replacing Br being a good leaving group, iodide being a nucleophile, it becomes a substitution reaction. And F, A, B, C, oh, this is D actually. And this is E. And F is sodium azide. This is called sodium azide. Azides are also good nucleophile. Azide in N3. So it's N3 minus is the nucleophile. Here I minus is the nucleophile. The product of that reaction looks like this. CH2, 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 an azido compound is formed. So by replacing Br as a leaving group, you are generating these compounds. So there is not much detail here. I'm just showing you just the products that are possible that could be formed in a substitution reaction using this primary alkyl halide. So this, by the way, it is only the halide is on a carbon that's only attached to one carbon. This is a primary alkyl halide. So in the meantime, I will also review things that as we move along, you need to remember. This is a primary alkyl halide, so there is no steric hindrance. It can just do the substitution without much of a problem because it's a primary alkyl halide. There is no steric hindrance. By backside attack of the nucleophile, you make a substituted products. So we'll pass to the next question. Okay, let's continue in the same line of questions. These are also very easy questions to ask you. What products would be formed in this substitution reaction? Everything that you see on the left are the electrophiles or the alkyl halides, and next to them is the reactants, which are the nucleophiles. So here water is being used as a nucleophile. Remember, we are using water now as a nucleophile. That would come over and over in any question. We have an acetate anion, which is a negatively charged, fully negatively charged. This is a neutral nucleophile. Water is a neutral nucleophile, where the acetate anion is a fully charged anion. Even though it's resonance stabilized, it still acts as a nucleophile. Here you have a dimethyl sulfide. Remember this. This is also another neutral molecule, but the actual nucleophile is actually the methyl sulfide minus anion. So I will give you the product and you'll start to learn the type or the nature of the nucleophile. Some of them, it's just kind of memorization of the nucleophiles. So I will just characterize what kind of electrophile we have. This is a tertiary type. I will also characterize the alkyl halide. So in the meantime, you study more of the concepts. This is a tertiary one. This is a secondary alkyl halide. This is a primary alkyl halide. So that's the nature of the alkyl halide is also important in the reactivity of the reaction. But right now, that's not the concern. We are just giving products. This is very simple. So if you remember, water could replace this. So that's the substitution reaction. So the product should look like this. OH2 plus, okay, that's the initial one. But at the end of the day, when you use water as a nucleophile, the product that's formed is water, because the H would be taken away by the I minus. So OH plus HI. Okay, so water as a nucleophile gives you an alcohol, meaning OH group. Implicitly, that's what happens, because one of the H would be abstracted again. But in this one, you have a chloride in the secondary position. So this is an acetate anion. Acetate anion is a resonance stabilized but fully negative charge. So it's somehow, it's not a very strong nucleophile, but it acts as a nucleophile through that oxygen. So the product looks like, let me change this. It's fading. So the product should be this. That means the O comes and attacks that carbon right there. This is the carbon that's being attacked, and the product is right there. So that's the carbon where the product comes. Here, as I said, this dimethyl sulfide nucleophile forms a nucleophile, which is one of the metal groups would be gone. So it would be, this is the nucleophile. It's not the whole thing. So one of the nucleophile, the actual active nucleophile is this. So the product that would be formed as S, it is through the sulfur, CH3. And the byproduct of this would be methyl chloride. So here the byproduct is just Cl minus. That's how we are given. Here the neutral molecule. So these are the products of the substitution of these 3 electrophiles and 3 nucleophiles. So this is important. Water is acting as a neutral nucleophile. Here a negative charge acetate anion used as a nucleophile. Here metal sulfide. So you could have sulfides of this nature, for example, SH is a nucleophile, metal sulfide is a nucleophile. So if you are also given in the reaction, if somebody gives you like this, the sodium is a spectator ion, which effectively actually produces SH minus. So as a nucleophile, this is a nucleophile. So the positive charges are not involved in the substitution reaction. So these are very simple questions, but the substitution products are like this. Here you are generating a tertiary alcohol from tertiary carbon. So it's a tertiary alcohol. This is a tertiary carbon now, right? This was because there was one hydrogen. Still, this is secondary. This is a primary as well. So in the substitution reaction, the mechanism of this electrophiles and nucleophiles goes through different mechanisms. We are not discussing that at this point, but what mechanism is generating that is different what mechanism produced the third one. So the mechanism of substitution for this is different from this one. Just to give you a hint, this upper one goes through an SN1 mechanism, because just a reminder, before solving this problem or before watching this video, you need to cover the lecture I have produced, because I will bring some of the concepts from the lecture. So before solving and looking at this video, you need also to have a good background. Here you have a secondary carbon electrophile. So this can go through SN1 or SN2, both. It's borderline because it is a secondary one. It could be SN1 or SN2, based on what solvents also are being used. Here, this is a primary. It should go not through carbocation type intermediate, because primary carbocations are not stable. It doesn't form a carbocation. This exclusively goes through an SN2 mechanism. So as I already mentioned, you'll be benefiting more if you have already read the video or watch the video which are on the lecture series of, I believe, 19, 20, 21. Those are the 3 lectures that were devoted for alkyl halide substitution reactions. If you really watch those videos and come to solve this problem or watch how this were solved, you will be really mastering the subject. So we'll continue to the next one. Let's continue this question session. This question asks you which molecule has a good leaving group. So there are compounds A to F, and your task is to identify which molecule really has a good leaving group for a substitution reaction. So a good leaving group is something which can handle the negative charge as it leaves, and also it should not be strongly basic, because it's a very strong base is rather a good nucleophile than a good leaving group. So these are the way how you would look at things. So in this first question, if you just look at here, obviously this is an alkyl halide. Most of the alkyl halides react as an electrophiles for a nucleophilic substitution, and obviously the chloride is a good leaving group, because chloride can carry a negative charge as it leaves. So Cl minus is a known, so as it can just leave as a leaving group with a pair lone pair electrons as a negative charge. The negative charge can easily be accommodated on a very electronegative chlorine anion. Here you have a hydroxide ion. So this is a very strong base. You know, OH minus is a strong base, and we have already said it's a good nucleophile. A nucleophile cannot be, a good nucleophile cannot be a good living group. That's how you should think in the future. So OH is not a good living group. So this molecule cannot do a substitution reaction without being changed into a good living group. So OH, an alcohol, without being treated by something which makes it a good living group, cannot be undergoing a substitution reaction. Reason being, OH minus, if you remember, OH minus is a very strong base. Very strong bases are also very strong nucleophiles. So the nucleophile tends to attach itself to the carbon, not to leave that carbon. So this would not be a good living group. So OH is not a good living group. So this doesn't have a good living group. Number B doesn't react as it is in a substitution reaction. Here you have cyclohexane. It doesn't have anything electronegative. Everything is hydrogen, right? Hydrogen cannot just leave. These are not reactive species. They don't react. Alkyl halides are like you have a sigma plus, a sigma minus polar bond that would be substituted. Here there is nothing that makes a polar bond on it. Everything is hydrogen on this cyclohexane. So there is nothing in this, it can be used as a good living group. So this molecule doesn't have any living group. So this molecule is called cyclohexane. It is an alkane. If you remember alkanes, they are not very reactive. They have to be converted into something reactive like alkyl halide before they start to react. Here, OH is a very strong base and a very strong nucleophile, so it cannot act as a living group. That's opposite. Here you have OH2, protonated water. This is protonated water. So the OH is now, you see here, exactly now this is the difference I want to show you. So OH, if we were to make it a good living group, meaning this one, the first thing is to make it reactive with a very strong acid. Okay, remember this. That means the protonation of the OH makes it into OH2 plus. That is a very good living group. It lives as a very stable molecule. What is that molecule? When this leaves, the living group would generate that, and water as a neutral, very stable molecule by itself. So OH2 plus, or a protonated hydroxide, if you were to make it into a good living group, you should react it with very strong acid. That reaction is called first protonation. Protonated. It makes it into good living group. This is important concept in substitution reaction. Remember forever now, OH2 plus is a very strong, a very good living group for a substitution reaction. So if somebody asks you substitute this with some kind of nucleophile, the first thing you should remember is OH should be first converted into a good living group. A good living group can be obtained by reacting it with a very strong protonating agent, which is a strong acid that would make it into water molecule that lives into a very stable good living group by forming a carbocation. Then the nucleophile, any nucleophile you have, can come and attack that carbon. Very important concept in these two questions. This is not a good living group, no reaction with this, but this one is a good living group. This one is a good living group. Now, let's continue with this. This is ethylamine, This is called ethylamine compound. It's an amine compound because it has NH2. Its name is ethyl. I'm teaching you as well a functional group. This is ethylamine, an amine compound. So if you just remember now, even it's very stronger base than OH minus. So NH2 minus is a very strong base. That's what we are contemplating. Is it a good living group? No. It is very strong base. Very strong base, bad living group. It will never leave. You cannot substitute that. It is even stronger than OH minus. So NH2 is much even greater than OH minus as a base. So it will never leave NH2. Okay? And iodide, this is alkyl halides. Almost all of the alkyl halides, we can use a certain nucleophile to make them a good living group because I minus is a good living group. It can be used as a nucleophile or also based on our condition that can be also a good living group. So I minus iodide in this alkyl halide, it's called propyl iodide. Almost all alkyl halides, they might have different degree of living ability, like fluorine versus chlorine versus bromine versus iodine. But in general, if you have an alkyl halide, it's most likely can undergo a substitution reaction. So this is a very important concept, especially when it comes to the alcohol and water molecule as a living group. OH2 plus a good living group. So if you were to react OH first, you have to do protonation to change it into a good living group. So we are changing it into a good living group by first reacting it with an acid. The acid would get it protonated. A protonated OH2 means it's water molecule. When it leaves, it's very happy for it to be living and live as water itself. So that's why it will be a good living group. So I'll continue with our questions. Here, the next question is asking to arrange in the order of increasing living group ability. Increasing. Order increasing. I think I missed increasing here. So you have different nucleophiles in a group, and we're going to arrange them in order of increasing nucleophilicity, group living ability. So the way I want to see this is based on basicity or nucleophilicity. It's the opposite. Here we are asked about living group ability. So since they are all negatively charged, if in normal times you'd consider them as a nucleophile, but now we are asked to live as a living group with their negative charge. So the pragmatic way of looking at this would be what are they? Are they strong bases or strong nucleophiles? The stronger the basicity or nucleophilicity, the lesser their living group ability would be. So the opposite. So if you look at here, the basicity of 1, 2, 3, the strongest base here is amide, because the free electrons and negative charge is available to coordinate very easily. So that is the strongest base. The next strong base would be hydroxide. The least basic one would be fluoride. So that means the order of increasing in living group ability would be NH2 is the least living group. It is less than OH. It's less than fluoride. So fluoride is the highest in terms of it's at least as a living group. Next is hydroxide, least is NH2. We have said that already in previous question. OH is not a good living group, so even NH2 is the worst. So the stronger as a base, the weaker as a living group. So increasing living group in this series would be, it's a relative term. So fluoride is the highest in terms of its living group ability. Here as well, NH2 is again, it is not a good living group. The next base would be OH in this, and the best as a living group would be now water. We know water is a good living group. It's a weaker base, and it's a weaker nucleophile than those, but as a living group, it's a good living group. So that's how we see it. In terms of here, you have bromide, anion, chloride, and iodide. So as a living group, if you just consider the acid form of this, the strongest acid is I minus, HI. HCl is the HBr is the next acid, strong acid. HCl is the lowest acid. That means the conjugate base of chloride is more basic. That means it's not a good living group. So Cl minus is not a good living group as compared to the other. The next weaker one is bromine. The next one is iodide. So it's increasing in this direction. So all of this direction is increasing living group ability. So they are good in terms of their living group ability as you go from left to right. So chloride is not a good living group. So that means it's more basic. So because HCl is the weakest acid, that means the chloride anion is the strongest conjugate base. Here we have ammonia, hydrogen sulfide, and water. All these are neutral molecules. So as a living group ability, ammonia is the most basic, stronger basic than water, and hydrogen sulfide is the least as basic one. So living group ability would be ammonia is the least, next would be water, and next would be hydrogen sulfide. That means hydrogen sulfide is a good living group because it's very weak base. It's not basic at all. So, but this one is the next basic one, and ammonia is the strongest base. So this is a relative term. You know, water was in one of the conditions the best living group in this group. However, in this category of nucleophiles or living groups, this is the order. So this is important aspect of understanding living group ability. So living group ability can be determined by how strong a base it is. If it's very strong base, it is a weak living group. So that's the opposite. If it is a strong nucleophile, it is not a good living group. So that's how I see it. So you can evaluate a living group ability or basicity. In that way, you could identify the property of your nucleophile or your living group and how fast the reaction could be. So we'll continue with the next question. The next question is, which reaction could take place as it is written here? So this is basically asking you how to identify the living group and the nucleophile which can replace the other one. So here you have amine group, which is a cyclohexylamine, and you have iodide, anion, as a nucleophilic substitution, NH2, it could not be a leaving group. It is a very strong base as NH2 minus. So it's much stronger base than I minus. That means NH2 is more nucleophilic than I minus. So I minus iodine anion cannot replace. That reaction would not take place. So basically what we are saying is this nucleophile is very weak to substitute the NH2. So as a substitution reaction, so which substitution reaction I should qualify this, saying that which substitution reaction could take place. So here NH2 is not a good leaving group, we know that, and this is not strong enough to substitute this. So this reaction as written cannot proceed. So the reaction cannot take place. That reaction cannot happen because this is very strong base. Very strong base. That means very poor leaving group. Reaction cannot happen. Okay, next one, I have metal iodide. It's an alkyl halide. You have a methoxide. It's called methoxide anion. Methoxide anion, because it's a negative charge. Methoxide anion, ethoxide anion, methoxides, alkoxides in general are very basic. We call them alkoxide. For example, they are represented by RO minus, alkoxides. Alkox, in general, they are called alkoxide. It could be a methoxide, ethoxide, bitoxide, and so on. So alkoxides are strong bases. Therefore, they will also act as strong nucleophiles. So if you just compare I minus here as a leaving group as a base versus methoxide, methoxide is very strong base. Hence, this substitution can happen just by attacking this carbon. You would substitute that, and iodide would be a good leaving group. Here, iodide minus is a good leaving group because it is weaker base. So this is a good nucleophile that can substitute the metal iodide, forming this ether. This functional group is an ether. I'm bringing several different concepts also here. So this functional group is an ether. So an ether is made from an alkyl halide and an alkoxide. The alkoxide would just kick out. So whatever, for example, if you are wishing to have diethyl ether, you'd use an ethoxide. If you want to use butyl ethyl ether, you use a bitoxide to replace that. So you make ethyl bitoxide ether. So this is ether functional group. Ethers are with oxygen linker. So that's an ether functional group. Here I have an alcohol functional group. Remember, ROH. So here ROH is an alcohol. Here ROR is an ether. I'm bringing different old concepts. By now you have already understood what functional groups they are. This is an amine functional group here. Here is a nitrile functional group. But anyways, coming back to the question, whether this substitution can happen or not. So if you just compare fluoride minus, fluoride and OH minus, which one is a stronger base? The stronger base is OH, hydroxide ion, anion, is a very strong base than fluoride. Hence, it cannot kick out that. So OH, as you know, is not a good leaving group. For OH to be a good leaving group, you have to protonate this, convert it into water, OH2 plus, that's when it can leave. But as it is written here, this reaction cannot happen because fluoride is a weaker nucleophile, weaker base than the OH minus. It cannot kick out the OH minus, so that reaction would not happen. Again, here we have CN, cyanonitrile, C triple bond N. It's a nitrile functional group. It's called nitriles, are CN containing functional groups. So you have 1, 2, 3, 4, 1, 2, 3, 4. This is a 4-carbon nitrile, and you have iodide as a nucleophile. So how do you compare this? To compare this, HCN, the acid form, HI, the acid form. HI is very strong acid. HCN is a weaker acid. Weaker acid. So if you have HCN and HI, it's just to compare. Therefore, CN minus is a stronger base as a conjugate. This as a conjugate is a weaker base. So the iodide cannot replace the CN. So that reaction cannot go as it is written. So this is how you compare them. Strong base could not be a good leaving group. Strong bases are good nucleophiles. So this is the kind of ways how you apply the concept of acidity, basicity, nucleophilicity, and all that to see whether that reaction can happen as a substitution reaction. So this is general. Still, we haven't reached to mechanistic way of looking at SN1 and SN2. So with this, we'll continue to the next. Okay, let's continue the questions. Now, in this question, you have an alkyl halide with the bromo. That's the primary alkyl halide. Alkyl halide. And the question is asking you what nucleophile for each one of those would be used with this to generate this product. These are the products after the reaction. These are products. These are substitution products. So if you are just given an alkyl halide, you are required to give what nucleophile would change this, into that, into that, into that. So how many nucleophiles you have to give? So I will put them as A product for B, for C, and for D. So there are 4 substitution final products. The question is asking you what nucleophile generates with this. So you have this. If you just look at here, what the question is basically asking you to retrosynthesize, retrosynthesize, and see what nucleophile is used. So this is a new concept in synthetic organic chemistry, but here I'll just simplify it. So what happened is this new bond is formed, if you just look at that. So that means Br was a leaving group, and here the nucleophile should have been so that nucleophile, if it attacks that, you can generate this. Again, here in this one also, retrosynthetically, if you look at it, the new carbon bond or the new carbon-sulfur bond was made right here. So that immediately tells you the nucleophile for this reaction was CH3, but with this negative charge on this carbon. So that's a new bond, where this is where it's happening. The substitution happens on the alkyl halide. Now come to this product. This should have been made if I have this electrophile or an alkyl halide, and if I break it down here, that's the nucleophile portion of it. So that nucleophile was maybe O, CH, CH3, 2 with negative charge, obviously. So this is a nucleophile for A, this is a nucleophile for B, this is a nucleophile for C. And again, now for D, the nucleophile should have been, so the carbon-nitrogen bond is where it's formed, right there, because this is where you are substituting it on this carbon, a primary carbon. So that nucleophile should have been N, CH3, 3, a neutral amine, neutral, because there is electrons that are being used to attack this carbon right here. That's why you have a positive charge now, because it's coordinated to 4 species together with 3 ones. That's why this lone pair of electrons were used to attack that. That's why it has a positive charge. So if you're to calculate a formal charge on this 4 coordinated nitrogen, you'll end up seeing a +1. But as a nucleophile, that's a neutral amine. It is called trimethylamine. So it's a neutral nucleophile with lone pair of electron, of course, neutral nucleophile. So all amines as a neutral molecule can be used as a nucleophile. So that is a trimethyl, because you have 3 of them. It is an amine, functional group, trimethylamine. So basically this is very easy question. You look at the compound you are given. This is alkyl halide, and this is a product. So you are basically asked to provide the nucleophile. So what happens is, for example, in the first thing, what you have done is you have Br plus SCH3 minus, giving me the product that was given. So that's basically you completed by providing the nucleophile by looking at the product you get. So this is in reverse, you are retrosynthetically look at what can be used to make this. So basically that's what you found out. At least one of them is given to you, which is alkyl halide, a primary cyclohexyl bromide. So now you can make from cyclohexyl primary bromide using all these nucleophiles 4 different compounds you can make. So that's the synthesis of these compounds. So we'll proceed into the next question. Okay, let's continue the question session. In this question, we have given 3 groups of nucleophiles, and the task is to order them according to increasing nucleophilicity. So we'll rank them according to increasing order of their nucleophilicity. So nucleophilicity goes parallel with basicity, as you know. So the more basic it is, the more or the stronger as a nucleophile it is. So first let's evaluate their basicity. So if you just look at this has a pKa value of about 30, 33, and in that range. Methanethiol around 10. Methanol we can say around 16 in terms of their pKa value. So basic, obviously it shows you the more basic would be methylamine. So it would be from the stronger side. Stronger nucleophile is methylamine, the strongest at least. The next one would be if we compare methanethiol with methanol. It is a methanethiol compound, which pK has is 10. That means it's very acidic. Relative to this, this is not as basic as this one. So methanethiol is much more acidic, and that means it's less basic than this one. So the next basic one would be methanol. So it's the next nucleophile, stronger nucleophile. And the lowest would be, as it is given, this would be a very weak nucleophile, as it is CH3SH, because this is stronger as an acid, if you just see the scale. Okay, so if we have all this, in the second series we have pure OH, that is a hydroxide anion. This is a very strong base, like sodium hydroxide, potassium hydroxide. The only thing you have to compare would be between fluoride and chloride. So if you just compare the acidity of HF versus HCl, you'll find that HCl is a stronger acid than HF. That means the conjugate base is weaker. Therefore, chloride is a weaker as a nucleophile than fluoride. So the sequence or the rank would be, the highest would be OH minus, followed by fluoride, followed by Cl. So chloride anion is actually a better living than acting as a nucleophile. So the way we are comparing this would be based on their basicity, because basicity also goes as a nucleophile. Here there is one concept that I want to mention here. If you have acetone, this is a polar aprotic solvent. Solvent is given as acetone. Acetone structure is, this is acetone. It is a polar aprotic solvent. That means it can only or mostly capture positive cations like sodium plus, potassium plus. So usually it solvates the cations, polar aprotic in general. And in your nucleophiles, in group A, you don't see any cationic species. That means they are neutral molecules. So this order I gave you here, regardless of being in acetone, still holds true. So we'll just keep this as is. Okay? So if there is a slight hydrogen bonding that forms with acetone in this and methanol, in that case the methanol would be coming into the lowest as a nucleophile. But mostly polar aprotic solvents actually coordinate with a cationic species. Here solvent is not provided, so the order is still correct here. And now we have the third group. You have ethyl sulfide, ethoxide, pure acetate anion in methanol. So first let's consider, without considering methanol as a hydrogen bonding species, solvent. This is polar protic solvent. So it usually solvates the nucleophile, not the cation in this case. polar protic solvent solvate the nucleophile by making hydrogen bonding. So we'll consider that fact, but let's first arrange purely by basicity here. So if you just look at acetate anion, that will be the weakest base, because acetate anion is a carboxylate, and that negative charge is resonance stabilized. Rather than going and attacking an electrophile or an alkyl halide, that is resonance stabilized. So resonance stabilized nucleophile is not as strong as you think it should be. So this is resonance stabilized. So that would be the weakest one. Now, if you consider these two, ethanol is pK of close to 10, and ethanol is about 16, if you consider the alcohols, the respective acids. So this is a strong acid, so it has a weak conjugate base. Therefore, the sulfide would not be a strong nucleophile, because its pKa is about 10. That means it is very, it's not very acidic as an acid, but the conjugate base, which is what we see as a nucleophile, be a weaker one. So it would be the next one. So it would be CH3, CH2, S minus. And the strongest would now become the alkoxide. Ethoxide would be the strongest nucleophile. So this is the order. The acetate anion is the weakest base, followed on the weakest nucleophile, followed by ethane sulfide, and also the alkoxide. So how about methanol? What is the role of methanol in this? So the role of methanol would make hydrogen bonding with this. Obviously, it would make it even much more weaker base and weaker nucleophile. Hydrogen bonding between sulfur and oxygen, if you just compare sulfur and oxygen, the most electronegative is this one. The most electronegative is oxygen, so it would make hydrogen bonding with this much easier. So considering it is run in methanol, now the order changes, because this will not be solvated by hydrogen bonding as compared to this one. So the order now would be, the right answer would be CH3. The acetate still remains as hydrogen bonded one, and also resonance stabilized, that is the least one, followed by methoxide, ethoxide, and followed by the sulfide. This is very important distinction now. This is without considering hydrogen bonding, without considering hydrogen bond. Say, if you are using this series, it will be correct if you are using it in, for example, acetone or some other solvent. But in polar aprotic solvent, polar protic solvent, like what we are given, the answer would be the last one. So it's acetate anion, followed by ethoxide, followed by the sulfide. The sulfide is the strongest nucleophile in this case. Polar protic solvent that would make hydrogen bonding. Hydrogen bonding is possible. Therefore, the order of the nucleophilicity is affected by what solvent you'll be using. So this is a very important question, and you need to revise, and you should review the notes associated with this subject matter. Polar protic solvents usually make hydrogen bonding, reducing nucleophilicity. In polar aprotic solvent, they coordinate with the cation, make the nucleophile much more available. So there is a distinction between polar aprotic and polar protic, and also we studied nucleophilicity of different forms. So we'll continue with the next question.